Welcome back, everybody. In this video, we will be covering the first part of Lecture 14. The topic is the Black-Scholes option pricing model. We're going to split this lecture into 4 separate videos. In the first video, we will provide intuition for the famous Black-Scholes pricing model. We will not do any formal mathematical derivations, but what we will see is that the Black-Scholes model takes the binomial model, limits it into a smooth state space, and then uses this as the basis for pricing. In the second and third videos, we will use the Black-Scholes model to price call and put options. We will show what the Black-Scholes formula is for calls and puts, and we will learn how to apply this in practice to derive fair values of calls and puts. And in the final part of the lecture, we will discuss implied volatility in the Black-Scholes model. Okay, let's get started. To motivate the Black-Scholes model, we'll start with a brief refresher of the n-period binomial model. In the n-period binomial model, we had 2 dates. Okay. The first date was date 0. This was today. Everything was known. And the final date was date capital T. This was when, say, option payoffs occurred. Now, in the multi-period binomial model, we assume there were n periods between these dates, or n intermediate dates that occurred between the two. Okay. Each of these periods was of length equal to t over n. Okay. In the multi-period binomial model, we had 2 assets as well, or 2 basis assets. There was a stock with a risky payoff and a risk-free bond with a continuously compounded risk-free interest rate of R. In each period, we assumed that as part of the binomial assumptions, the stock price could either move up or down. So for example, at date 0, the stock price either moved up or down. If it moved up, it increased by a factor of U. If it moved down, the stock price decreased by a factor of D, which was 1 over U. Okay. In each period, this movement could occur again. So after the first period, the stock could either move up or down again, depending on the state. So if we were in the U state, it could either move down or up. In the down state, it could either move up or down, and so forth, building this all the way out into the final dates at the very end. Okay. We saw that the terminal stock price at the end of these dates depended on the number of up or down moves. This determined which terminal state we were in. So given a number of up moves, you could always calculate the terminal stock price. For example, if the stock moved up I times and it moved down conversely n minus I times, the terminal stock price was just a function of the number of up moves, S sub capital T of I. It was equal to U raised to the I power. It moves up I times, each time compounds U on top of it, times D to the n minus I power times S0. And given a path I of up moves, we could also calculate the risk neutral probability of that path. For example, if the stock moved up I times and down n minus I times, the risk neutral probability of this path occurring was n choose I, qu to the I, 1 minus qu to the n minus I. That is, the number of up moves I was a binomial random variable, and we know that binomial random variables have probability distribution functions or mass functions given by the below. Okay. Binomial model is awesome. It can accommodate all sorts of exotic derivatives, and it can even incorporate things like American options and path-dependent options. Okay? The only drawback of the binomial model is that it lacks in realism sometimes, in that it's a discrete time model. In reality, time is not discrete. Time is rather smooth. It's a continuum. And hence, to increase potentially the realism of these models, people would like to move them into continuous time to be more representative of reality. To move the binomial model to continuous time, all you have to do is ask the following question. What happens if we choose a really large number of periods to break up between these two dates, 0 and t? So for example, instead of having these, say, like whatever it is, 8 dates here, what if we choose the length of time to be very small, such that you have a huge continuum of states until this becomes unreadable in some sense? So you want the length of time t over n to essentially approach 0, or equivalently for n to approach infinity to give you a smooth state space. It turns out that if the number of periods grows large, then everything at the terminal states will start to smooth out. And instead of having a discrete set of states at the very end, what you're going to have is a distribution of stock prices, or a continuous smooth distribution. Okay? Under reasonable parameterizations, this distribution is going to be normally distributed, and the stock price is going to follow a log normal distribution, which will in turn imply that log returns on stock prices will be normally distributed if we take the binomial model and limit it essentially into infinity, make it very smooth. Okay, so if you take the binomial model and you move it towards continuous time to match realism, to match reality, what's going to happen is that stock prices are going to start to follow a log normal distribution. They're still going to be bounded below 0. And at the same time, returns are going to follow a normal or a bell-shaped distribution, okay, under the risk-neutral probability measure, of course, with a mean return of r minus 1/2 sigma squared times t as the mean, and a standard deviation, okay, a 1 standard deviation equal to square root sigma squared times t. So under the risk, if we move the binomial model to continuous time by shrinking the length of time between each of the periods, or equivalently by selecting an infinitely large number of periods, what's going to happen is that the terminal stock prices are going to follow a distribution that's log normal, or at the same time, returns are going to follow a normal distribution under the risk neutral measure. That normal distribution will have two parameters. It'll have a mean and a variance. The mean will turn out to be r minus 1/2 sigma squared times t, and the variance will turn out to be sigma squared t. All this means is that if we choose a very large number of periods in the binomial model, it's going to be equivalent to making the assumption that returns are risk neutrally normally distributed with the mean and variance given below. Okay? It turns out that the very famous Black-Scholes option pricing model is nothing more than a model that just assumes that returns are normally distributed under the risk-neutral measure. Okay? So the Black-Scholes option pricing model, which is very famous in practice, is just a model that assumes returns are risk-neutrally normally distributed and then prices European call and put options under this assumption. Okay? Essentially what Black-Scholes does is it takes the binomial model, limits it into infinity, makes it a smooth continuum of time. This is equivalent to assuming a normal risk-neutral distribution of returns, and then it wants to say what is the price of call and put options. Okay? And the way it's going to do this is just by doing this very simple F-tap. It's going to say you want a price of call. It's the expected risk-neutral discounted payoff, okay, of the call. Okay? And the only thing that Black-Scholes is going to have that's new and different is that it's going to assume that the returns that go into computing this expectation are risk neutrally normally distributed instead of, say, binomially distributed like we had in the previous lecture. Okay? Black-Scholes is going to be super important in industry. Its extensions are more so used than anything else. So extensions such as the Heston model and the stochastic volatility models are used in industry, but Black-Scholes is still very prominently used in terms of quoting conventions and in other fields such as executive compensation contracting. It's so famous and had such a big impact on option markets that its creators, Fisher Black and Myron Scholes, along with Robert Merton, who really showed this risk-neutral properties of the model, won Nobel Prizes. Black won it posthumously because he had died. Okay. So that wraps up this first part of this lecture. We basically motivated Black-Scholes. Black-Scholes is a very famous option pricing model. It takes the binomial model, tries to make it a little more realistic by moving it to continuous time. And that continuous time assumption is equivalent to assuming a risk-neutral normal distribution of returns. Okay, what we're then going to see in these next couple lectures is how to price options using this Black-Scholes model, and then to learn about something called implied volatility, which is a very important piece of this model. Let's take a quick break and we'll resume the lecture in the next video.